that respects these equations. And so there are not so many bijections. You try them all out, and then that's fine. You either find something or you don't. And if you don't find something, then in order to cover also these cases, you have to realize that the pi doesn't have to be a bijection. That's sufficient, but it's not necessary. What you really need is a search action, because you want to hit every root. But if there's one root that you hit twice, that's okay. Then that means you are in this case, where the 6 has to be hit twice. This may be necessary. So this is what we do. We go through all the pi's and check, so all the surjective maps, pi, and check whether if I assign them in the way, these equations are satisfied, and if yes, this gives the rise to the factorization. Okay. Any questions?
The fact that you took P1 equal to 2, P2 equal to 3, and then you repeated the same root, does that not contradict your square-free assumption?
No. Because this polynomial is supposed to be square-free. This is what the assumption is. And then it happens to have such a factorization. So it's not that when you have something like this and you multiply it, that you would get here a square. That doesn't happen. The square would mean something different.
So it's square-free in the usual sense.
It's It's square-free. It's square-free in the usual sense. Not with respect to this product. It's square-free with respect to the times product. Sorry, I should have said that not here. All right. Any other questions? Aha. So what else did I want to say? So there are now some technical some technical things that you can do to improve the search for a pi, because there are still a lot of pi's, and if you want to try them all one after the other, you will spend a lot of time. So you could do something, but this is a bit technical, and I don't really want to explain it. So I just mention it, that what you really do, if you have a pi, and maybe this goes in general like this, 1 to m, to 1 to k, and then these are big, perhaps, and you build this up. Step by step. So you start with 1 times something to something, and then there are not so many possibilities. So first you can say that the 1 is always mapped to 1, because you can normalize you can say that the numbering of the phi's and the numbering of the psi's, we don't care about their permutations. We can make a canonic choice here, and then this cuts down some possibilities for the pi's. And then also you can say, okay, I'm determining all the partial maps that start with 1 here, and then I try to extend them to a map that sends the first 2 numbers to something. And it turns out that there are not so many possibilities. So this 2 can be mapped to any of these numbers, but once you choose, you make your choice there, then this limits a lot of further decisions of how the pi could look like. And in many cases, it turns then out that there's no way that this 2 gets mapped to this k. So you would notice this early on in the search. So you would have a search tree for the pi where most pi's die here, and you don't need to go here because you know there's nothing. And so in fact you will spend most of the time at the top of the search tree, and only where there exists something, they will go down all the way until you find the pi that is the factorization. So it's in the end just a simple search, and it's therefore an exponential algorithm. But in practice, it works more reliably than you would expect, because you don't consider most of the search tree you can cut away by doing some tricks that I don't want to explain in detail, because they are not suitable for a talk. Well, maybe then that's it.
Maybe
You have a question?
Yeah. So, how far can you do it with applications? to the
Ah.
icing.
Okay, so we can, I don't remember exactly how far we got, but it, so maybe a product with 10, or roughly 10, something between a little lower than 10, maybe 8. So that would be an input sequence of order 2 to the 8, and we would break it into 8 sequences of order 2. So this works. But since you're asking for the application, the one thing that still bothers me a little is that this factorization is not unique. So if you have this factorization, you could easily make another factorization out of it by entering another factor here, x minus 3 times x minus, what's your favorite number? Yeah, okay. Times x minus 1 over 11, x minus 2, x minus 3. So this corresponds to saying that if f of n times g of n is h of n, and you have found such a factorization, and you could also say f of n times 11 to the n times 1 over 11 to the n, g of n, and that would be another factorization. Okay, so that's also something that we have in the usual factorization. But here it's not, in our application, it's not so obvious what is the right one. So you in the usual factorization, you would make the things monic, and that's the right thing. But here it's not so clear that this is the right thing, because when I factored the polynomials that we get, then we get here really ugly algebraic numbers that have high degree minimal polynomials, and they are then the stopping that they prevent me from going further. It's not the search that costs too much, but it's the algebraic number arithmetic. And with these algebraic numbers floating around there, they don't only prevent me from going further, they also prevent me from recovering the Onsager formula, because this one doesn't have algebraic numbers. So he somehow not only found the factorization, but he also found the right normalization. And that's something that we still have to look at. How to find. Other questions? Yeah?
Is there anything appreciably different with this algorithm if you do have repeated factors, or is it just you also have things that show up with n's in front of them?
Right, so if you have repeated factors, then you would first factor the square free part, and then assign the exponents. There are not so many possibilities for the exponents, so you can do that in a post-processing.
Is there any hope to extend it to factorization of P recursive sequence?
Aha. P recursive sequence, so there. I don't know how to do this, but there's an algorithm by Mark van Hooy. And his student, Korean, Young, Jae, Cha, something like this. Is this on tape? Okay, maybe like this. I don't know, but they have looked into this, and they can factor in this sense operators with polynomial coefficients, but they have a limitation on the order. So they can factor, I don't know, 6 order operators or lower, but I think, if I'm not mistaken now, it's not a general procedure that works for arbitrary order. There's another work in the literature from Singer, and also a student whose name I forgot now, and they do it for the differential case. So for differential operators, also with polynomial coefficients, and I think they do it with arbitrary order. But it's more complicated than what we are doing there. There's also an algorithm from Ritt from the 1930s, and he solves exactly our problem, but also in a more complicated way. And not just more complicated, but also less efficient.
Thanks again. Beautiful.
Sorry for being under time.
Better under time than over time. If you'd like to join us for dinner, please let me know right now.